Good day. We're looking at 5 electron pairs. We'll start with AX5 and we'll gradually replace those atoms on the outside with lone pairs until we get down to AX2E3. So that means this PowerPoint video has 3 slides that you'll view. It's one of our longer ones. These things all have to be violators because by the time you have 5 electron pairs around the central atom, you're looking at 10 electrons, more than 8, which is the octet rule. So for anything that has 5 electron pairs or more, I have to tell you it's a violator and give you some clues about the structure. So we look at PCl5, and it's a violator. We know a phosphorus has 5 valence electrons, and so sometimes it gets involved and ends up with all of the electrons being involved in bonds. You'll see we haven't bothered the lone pairs around all the chlorines in the diagram. We're interested in these kinds of bonds here and what things are involved in bonds directly to the phosphorus. So here's what the shape looks like. If we think of it as the Earth, this would be like North Pole, this is South Pole, and then these 3 things are all part of the equator. So we end up with a triangle around the middle, and then it points up and it points down. So trigonal equator, triangle in the middle, bipyramidal. We have a pyramid here and we have a pyramid at the bottom. Bi means 2. So if I was trying to draw this as a structural diagram, I would do something like this. I'd go start by putting a chlorine up, then I go straight down and put a chlorine. Believe it or not, that's supposed to be a C, that's supposed to be an L, and then I can put a Cl straight out on this side, and then I have these like so, and I'm trying to show that these are in the equator, like these ones, and then a chlorine up and a chlorine down below. So a very odd shape. You won't run into it very often, but it is totally fair game when we get around to a test. And you can see what we're going to do is we're going to have to replace one of these atoms with a lone pair of electrons. And the decision is, do we replace in the equator or do we replace at a pole? Well, if I replace at the pole, what I'd get is a 90-degree angle between 3 atoms and the chlorine. On the other hand, if I make this a lone pair, then I get 90 degrees between 2 of them, and I get a bigger angle. So I minimize repulsion if I replace electrons, lone pairs, in the equator. So it'd be first I'll wipe out this one, then that one, then that one, and we will be done. There's our space-filled molecule, delightful stuff. The Michelin Man has arrived. So our next one is TCl4, distorted tetrahedral. I prefer to call it a seesaw, and you'll see when we make the shape of this with the ball and stick models, it does behave that way. So what we're saying is we have the chlorines, 4 chlorines, but right here we have an extra lone pair, and that's the E around the central atom. That lone pair distorts it from being a regular tetrahedral shape. So here we've replaced an atom with a lone pair, and when you watch the next video, when we see seesaw, if I turn this to 90 degrees, all of a sudden I'll see that it actually looks like a seesaw shape. When I go to the next beast, so here we are, so if you turn your head 90 degrees to the right, then you can see this thing can bob this way, that bob that way, and be a nice teeter-totter or seesaw. Next place I'll replace the lone pair will be one of these 2 characters that's in the equator to get my AX3E2. So ClF3 is a violator. Again, we're not worrying about all lone pairs around the fluorines. We know they'd have to have the octet. So 1, 2, 3 bonds. And what I really am saying is 3 atoms bonded right to the chlorine. That's the AX3. Lone pair, 2 lone pairs on the central atom. And you can see if I'm drawing this, I cleverly go Cl, and I would go and say, okay, I'll stick an F straight up like that, stick an F straight down like that, and either to the left or right, I'll put another fluorine. And this is a shape we find. And so we find, that's a terrible F. So we find it's 90 degrees between those two bonds, 90 degrees between those two bonds, 180 degrees between those. If you turn your head 90 degrees to the left, suddenly it has an accent. It will look T-shaped. And our last one, there we are. There's the two lone pairs that we haven't shown. There's the fluorine sticking out. Our last one will be AX2E3. So now all of the bonds in the center, in the equator, have been replaced. And very hard to see, again, we have our octet. Well, we have more than octet. We have a dectet because we have 10 electrons around, 2 involved in bonding, 2 involved in bonding, and then 3 lone pairs left off around the center iodine. We treat one of the atoms of iodine in being in the middle. And so I can say, okay, I've got an I like this. I have an I like this above it. I have an I down below it, and we don't include lone pairs when we do our structural diagrams. And then I say, oh, it happens to be 1 minus, so I just go thump, put in my square brackets, and put in my 1 minus, and something should be showing up. So there's all lone pairs, leaves behind a linear shape. And this is what it will look like as a ball and stick model. A nice linear structure, 3 iodines in a row. So that was a beast because we had 4 different structures to deal with as we went from AX5 to AX2E3, all of which were violators of the octet rule, which means all had more than 8 electrons around the central atom.